how many chains? Which is made of 3 chains. And they are given a designation of alpha chain. They can be alpha 1, alpha 2, alpha 3, all the way to I don't know how many, like 30 so far. And you can have combinations of these alpha chains. You can have alpha 1 with alpha 1 and alpha 1. You can have alpha 1, alpha 1, alpha 2. So different combinations that exist in different tissues. And we said that it has a helical structure. And then we talked about the primary structure. And we said that about 1/3 of all amino acids are glycine. And the purpose of glycine is, it is small, it fits into the core of the alpha chains, so it packs the molecule. There is no repulsion, there is no steric hindrance between glycine residues with other molecules, other amino acids. All right. And we said that about 25% of the primary structure of collagen is proline or hydroxyproline. In the book it says it's about 30%. But let's say it's about 25%. So you have proline and hydroxyproline. And we said that the purpose of proline is basically 2 things. What are they? Kinks, yani ish. What does it do? It creates the helical structure by creating these kinks. That's one. That's function 1. But function 2, purpose 2, it's a rigid amino acid, so it makes the molecule rigid as well. Great. And then we said that you have hydroxylysine, right? What's the purpose of hydroxylysine? Glycosylation. So collagen is a glycoprotein. And then you have some lysine residues as well. What do lysines do? Cross-links, covalent cross-links. And this happens only when lysine becomes oxidized, replacing the amino group with an aldehyde group. So it is an aldol. It is it's called all-lysine. And that's what creates the covalent cross-links between the different oxidized lysine residues. And then there is hydroxyproline as well. What does hydroxyproline do? Hydrogen bonds. So all of these collectively, they make the molecule, the tropocollagen, really packed and rigid as well, serving the purpose. And to illustrate the importance of hydroxyproline is what's shown in here. What's shown in here, we have this plot. Showing collagen with no hydroxyproline versus normal collagen containing hydroxyproline, where the collagen without the hydroxyproline, it becomes fragile. It breaks up easily when the temperature increases. Even at normal temperature, this collagen molecule is not really stable. Okay? Now, another illustration for the importance of hydroxylation of proline is the disease scurvy. Scurvy, also in Arabic it's known as isqarbut. It usually affected in the past sailors because they didn't eat fruits. Fruits didn't last for long. So they didn't eat fruits. So what? Well, fruits contain vitamin C. So what? Vitamin C is important for the function of the hydroxylase enzyme, the proline hydroxylase, the enzyme that hydroxylates proline to hydroxyproline. So there is deficiency in the amount of hydroxyproline in collagen, resulting in formation of weak collagen molecule. As a result, anything that depends on collagen becomes fragile. It breaks up easily. So you have the gum is affected, so teeth fall off by themselves. Blood vessels become really fragile as well, so they rupture easily. Skin as well, so people would get injured easily as well, and so on. This is why in those pirate movies, you always have these sailors, you always have this joker sailor that laughs, and you see that this person doesn't have any teeth. Why? Because of scare. Okay. So that's collagen. Now let's talk about elastin. Elastin is a little different than collagen. Now, when you see a little baby, nice cheeks, right? What do? You grab him and stretch, right? Nice, and you play with him. Nice. But it never comes out with your hands. Why? Because there's collagen. Well, why do they stretch then? The collagen is rigid. They stretch because there is elastin. So in tissues like cheeks, for example, blood vessels, another example, you have a combination of collagen as well as elastin. Collagen provides stability, rigidity of the tissue, and elastin provides flexibility. That's why you see blood vessels, when blood is pumped into blood vessels, they stretch because of elastin, but they never rupture because of collagen. So it's a combination of these two things. So basically, you have the elastin molecule. Normally, elastic fibers, they look like this. They can be stretched, but they never break up. Why? One, because there is collagen, and two, because these are also cross-linked to each other, these elastic fibers. But then once you release that stretching effect, the tissue comes back together like this again. So it's different than cartilage. Remember when we talk about cartilage, I said cartilage exists in joints, right? And I said that when you jump, your bones do not hit each other because there's cartilage that can be compressed, but once you release that pressure, what happens to cartilage? It stretches back, becomes relaxed. Why? Because of the negative charges. Well, it's the opposite here with elastic fibers. Elastic fibers are really compact, but then they can be stretched. But once this is gone, this effect is gone, they come back together. Why? Because elastin, the protein, is a hydrophobic protein. So when these amino acids get away from each other, they come back together, just like any other hydrophobic protein. So when we talk about protein formation, we said that these hydrophobic amino acids, they get together because they don't like each other, they only hate water. That's what's common between them. They hate water, and that's why they cluster together, hiding in the middle of a protein, in the core of a protein. Fine. So elastin is the functional molecule. It is highly hydrophobic. It's rich with proline and glycine. It contains hydroxyproline. So what does that create? Hydrogen bonds, but it does not have hydroxylysine, so it is not glycosylated. So it is not a glycoprotein. Now, also the primary component is known as tropoelastin. There are cross links between lysine residues, just like collagen. So this is like one classical question that we usually ask in exams is, one of the following is not a difference between collagen and elastin tissues. Okay? So these are the differences in terms of hydroxylysine, hydroxyproline, lysine cross links, hydrophobicity, and so on. Collagen molecule is also a bit hydrophobic as well. It contains proline and glycine. And that's why that helps also compacting the molecule, packaging the molecule, getting the three chains linked to each other or close to each other. So if you look at the primary structure of elastin proteins, they are composed of hydrophobic segments, and that's what makes the molecule, the chains, close to each other. That's one. And the other thing is, and it gives the elastic property. Also, it's rich with alanine and lysine, creating the cross links between the different chains, just like collagen. So this is elastin. So let's talk about keratins. There are two types of keratin proteins, known as alpha and beta. We are concerned with the alpha keratin in this lecture right now. The alpha keratin exists in different types of tissues, like hair and fingernails. So someone would say, well, what was right? But these are two different tissues, and they contain alpha keratin. I mean, fingernails are tough, rigid, right? Solid, and hair is flexible. Well, yes, the difference is that in fingernails, there is a lot of disulfide linkages between the cysteines. That's what makes the tissue tough and rigid. Whereas in hair, there are less disulfide linkages between the cysteines. And they are different among people. So you see someone with flat hair, smooth hair. This means that there is little disulfide linkages between the different keratin molecules. Whereas Africans, for example, you have their hair kinky, which we call farafin. So you have the hair kinky and rounded. Why? Because there are a lot of cysteine linkage or disulfide bonds between the different keratins. When you see someone with wavy hair, this means that there is some disulfide bonds between the different keratins. So how does a single hair look like? Well, if you look at a single hair, it's made of, if you zoom in, it's made of macrofibrils. Hundreds of these. Now these macrofibrils are made of microfibrils. And microfibrils you have 8 of them in here. Now these microfibrils are made of protofibrils. Now these protofibrils are made of dimers, of chains, of the alpha keratin chains. So the basic structure is a dimer of alpha keratin chains. So you have these 2 dimers. They form, two chains forming a dimer. Now when you have 2 of them together, this is known as a protofibril. When you have 8 of them, this is known as a microfibril. Now when you have hundreds of them, you have what is known as a macrofibril. And then when you have many of them, depending on the thickness of the hair, you have a single hair in here. So this is all an alpha keratin. It's all alpha keratin. And I said that the difference between fingernails and hair is the level or the amount of disulfide bonds between the cysteines. So you have a lot of disulfide bonds within a fingernail, and that's why it has this rigid structure. So again, this is like differences between these fibrous proteins in terms of how crosslinks are formed with elastin and collagen fibers. They're formed between lysines, but for keratin, they're formed between cysteine residues. Okay. So this just to show you that women, and these days, even guys, they would do anything to look beautiful. They go into the beauty salons looking like something, and they come out looking totally different. In the past, it used to be their hair. Now it's everything with Botox and whatever. So the idea is, let's link biochemistry to real life now. Why is it that you see someone going into a beauty salon with smooth hair, and she comes out with totally different look for that hair? Looking curvy, nice, and whatever. So, or you see someone with curvy hair, she goes in, she comes out with smooth hair, with no kinks whatsoever. And you have what is known as a perm, right? Perm comes from the word permanent, meaning that you have this wavy hair and it lasts. It lasts for a long time. Until when? Until then? Until new hair comes out. The natural looking hair comes out. So how is sperm done? Why is it we go to the, we take a shower and our hair becomes nicely smooth, and then after 5, ما راح تقعدي بالمحاضرة مطولة، فراح حاسب الغياب. يعني انك تقعدي 10 بنتي انت جيتي متأخرة صح؟ ما سمعتيني أول المحاضرة صح؟ لو سمعتيني كنت ما سألتي هذا السؤال. الله معك. Okay. So what does happen exactly with hair? The last thing I said. So in the morning when we wake up, our hair is all wrinkly and messy and whatever, right? So we are in a hurry. So what do? We wet our hair, right? And it becomes smooth. And then after 10, 15 minutes, it comes back again, reforming the same sort of messy hair. So what does happen? You see someone going into an interview. What do they do before they go into the interview? I was with that. They do this, right? That's what they do. Well, so what has happened? Why do we do this? Well, there are two things that happen. There is perm and there is temporary formation of hair. Well, what happens with the temporary reformation of hair is that you break the hydrogen bonds between the keratin molecules with water. So when you wet your hair, you're breaking the hydrogen bonds, and that's it. And then after 10, 15 minutes, when water dries up, what happens? You have reformation of these hydrogen bonds, and hair becomes sort of messy again. That's why you see women, for example, when they go to parties, they take showers, they roll up their hair, and then they dry it up with the hair dryer, and then they go to the party. And then they dance or whatever, and they sweat, and their hair becomes messy again. But you know, after a few hours, they go back home, they take a shower, and their hair becomes normal again. Again, what happens? Reformation of hydrogen bonds between the different keratin fibers. So you have that. But you have something known as a perm. Now what happens with a perm, you see this woman with a smooth hair, she goes into the beauty salon, and what happens is that they break the disulfide bonds. They reduce the disulfide bonds. They reduce the cysteines. And then they roll up their hair or do whatever, I don't know, I've never been there, but they roll up their hair and then they re-oxidize the disulfide bonds, reforming these linkages, covalent linkages, and that's why the hair stays as is for a long time until new hair comes out again. So that's why it's called permanent, because it lasts for a long time. Now some people, they have this kinky hair, really wrinkled hair. What they do is that they want to make it smooth. So they break the disulfide bonds and they keep it as is. So their hair becomes smooth. There's a very beautiful movie. I really encourage you to watch it. Malcolm X. I don't know if you've seen it or not, but it talks about this great person, Malcolm X. Now, in one scene early in the movie, in the 1920s, now he was a black person. And blacks, just like us these days, we are defeated. We feel defeated psychologically from inside. So we always want to look like the victorious group, right? Which is Westerners these days. So we talk like them, we behave like them, we wear whatever they wear, and we want to look like them because they are the victorious. So Malcolm X in the 1920s and his friend, they wanted to get rid of their wrinkly hair. So what they did in that movie is that they put hydrogen peroxide to reduce the disulfide linkages, and that's what they did. So their hair became smooth. Watch this movie, please. So that's the idea, is that you have, with a perm, again, you have smooth hair, reoxidation of the disulfide bonds, it becomes wrinkly, or if you have wrinkled hair or wavy hair, it can become smooth again by breaking the disulfide bonds, and this is this is the pair. That's what we call a pair. Okay? So that's biochemistry in real life. Questions? So let's talk about globular proteins. And we have 3 globular proteins that we want to talk about. And they are myoglobin, hemoglobin, and immunoglobulins. We'll talk about these myoglobin and hemoglobin in this lecture. Now, myoglobin and hemoglobin, there's something common between them, is that both of them are bound to a heme group. And that's why hemoglobin is known as hemoglobin. Now, heme group allows these 2 proteins to bind to oxygen. That's what it does. So they both bind to oxygen. But the purpose is different. For myoglobin, from the name, myo means muscle. So the purpose of myoglobin is to bind oxygen and store it, so that oxygen is released only in cases of emergency, which are what? Hypoxic conditions. That is when there is low level of oxygen in muscle tissues. Hemoglobin has several functions. The main function of hemoglobin is to transport oxygen. So it binds to oxygen in lungs, it goes to peripheral tissues, and it releases oxygen. That's what it does. But hemoglobin has 2 other important functions as well. One of them is binding to CO2, carbon dioxide, in tissues, peripheral tissues, grabbing it and releasing it outside. Exhale oxygen as carbon dioxide. And the other function is blood buffering. We talked about it before. Since there are a lot of hemoglobin molecules in our blood, and hemoglobin has these amino acids with R chains that can bind to protons and release protons, they can play a very important role in blood buffering. So these are the different functions of hemoglobin. Now, hemoglobin and myoglobin, both of them belong to a group of proteins known as hemoproteins. That is, proteins that are bound to a heme group. And this heme is bound to these proteins covalently. And they are called, and heme is known as prosthetic group. So the definition of a prosthetic group is, it is a non-protein, organic molecule that is covalently bound to proteins. Okay? So proteins are, such proteins are known also as holoproteins. Remember the definition of holoproteins? Proteins that have non-protein groups attached to them. Without the heme, they're known as apoproteins. And heme is a prosthetic group. So let's look at the structure of myoglobin first. Myoglobin is a monomer. It's made of one polypeptide chain. So it has primary structure, secondary structure, tertiary structure, but it does not have a quaternary structure. It is full of, it is a globular protein, meaning that it looks rounded, like a ball, that's one, and just like any other globular protein, it has the hydrophobic amino acids hidden in the core of the protein, and you have on the outside of the protein the polar and the charged amino acids, primarily, just like any other globular protein. It's full of alpha helices. In fact, it has 8 alpha helices. So you start with this protein right here. That's the N-terminus, amino acid number 1, number 2. So we know the position of every amino acid in myoglobin. Here you have the first alpha helix. And these alpha helices, by the way, are given a designation as alpha helix A, alpha helix B, C, all the way to H. So here you have alpha helix A. Then you have a turn, and then you have, in the back, you have alpha helix B. Then you have a turn, and you have alpha helix C. A turn, D. It goes down. Here you have E, F, goes right in the back, G, a turn, and then finally you have H. So that's the structure of myoglobin. It's full of alpha helices. Right in the middle, you have the heme organic molecule. Okay? So again, just like any other globular protein, you have the hydrophobic amino acids inside, the hydrophilic amino acids to the outside, except for two histidine residues. One of them exists in alpha helix F, and the other one is located in alpha helix E. And they surround the heme molecule. So this is the heme molecule right here. That's heme. It's a flat molecule. It lies right in the middle of the hemoglobin molecule. Now, so right inside, you have hydrophobic amino acids except for two residues, two histidines. You have one here on the F alpha helix, and you have another one right here in the E alpha helix. And they are known as the proximal histidine, and the other one is known as the distal histidine, because you have one that is close to the heme, that's the proximal histidine, and you have one that is a bit relatively far away from the heme, and it's known as the distal histidine. Right? And these two histidine residues are surrounded by hydrophobic amino acids. And there's a reason for why there are histidine residues, and there is a reason for why they are surrounded with these hydrophobic amino acids. And that's the beauty of biochemistry. So let's see. So right here we have the heme molecule right here. This is the proximal histidine. The purpose of the proximal histidine is to bind to the heme group. So let's look at the heme group actually. So this is how it looks like. This is heme. So heme is this structure right here. It's made of 4 pyrrole rings. 1, 2, 3, 4. That's the name of the ring structure. Pyrrole. And these pyrrole rings, each one of them is bound to an iron in the middle. Now iron can make 6 covalent linkages, 6 covalent bonds, and they are known as 6 coordinates. So you have 4 of them exist between iron and the pyrrole rings. The 5th one exists between the proximal histidine and iron in the middle. Yes? So there's one left. This one exists, or it can form, between iron and oxygen. So the 6th coordinate exists between iron and oxygen. Now, the distal histidine, its function is to act as a gate. So like bawabah. So it acts like a gate. What it does is that it opens up, allowing for oxygen to go in and bind to iron, or it closes off the entry of any other molecules to inside the myoglobin molecule. Hey. So let's talk about iron now. Iron must, in order for iron to be functional, it has to be in the ferrous state. That is, it has to be reduced. It has to be Fe plus 2. If it is Fe plus 3, if it is in the ferric state, it's not functional. It cannot bind to oxygen anymore. So it has to be kept in the ferrous state. Wait. Now, because it's always in the ferrous state, it gives blood a nice red color. If it is in the ferrous state, if it is in the ferric state, if it is in the ferric state, then it cannot bind to oxygen and the blood color would be blue. That's why you see this royal family, the British royal family, having a blue color, a blue blood color, and they say this is the royal color. This is so unique for elite people. Well, this is baloney because that's a disease. It's basically that iron cannot be reduced from the ferric state to the ferrous state, and as a result, it cannot bind to oxygen, and that's why blood looks blue in color. So, but then when iron binds to oxygen and it releases this oxygen, iron becomes oxidized. It converts from the ferrous state to the ferric state. So how come oxygen doesn't become oxidized? How is it possible that it's always in the ferrous state? How is it possible that it's always Fe+2? That is, it's always capable of binding to oxygen because it is surrounded by hydrophobic amino acids. So what happens is, when oxygen is released, there is no oxidation of iron because the hydrophobic amino acids that surround him, they donate, there is electron rearrangement so that an electron transfers from these hydrophobic amino acids to iron. So iron is kept reduced all the time. So that's the purpose of the hydrophobic amino acids in the molecule. So now we know what the function of hydrophobic amino acids is. We know what the function of the proximal histidine is. Well, how about the function of the distal histidine? I said the distal histidine acts like a gate, right? Allowing for entry of oxygen inside. But there's something else that it does. What it does is that this distal histidine, because now it's close to oxygen, notice that the interaction or the bond between oxygen and this iron or oxygen is kept at an angle. It compromises the affinity, it compromises the interaction between oxygen and iron, meaning that it becomes easy for oxygen to be released. And that's good. Yes, we want myoglobin to bind to oxygen, but not release it. It has to be able to release this oxygen when the level of oxygen becomes really low. Yeah? So that's a purpose of the distal histidine. But there's something else that distal histidine is important for. Now, you have carbon monoxide. Carbon monoxide really looks like oxygen molecule. Looks like O2. Now, if you have free heme, that is, it's not bound to myoglobin. If you have free heme, and you add equal amount of carbon monoxide, CO, and oxygen, carbon monoxide binds to iron with an affinity that is 25,000 times higher than oxygen binding to iron. Amazing. So this means that if there is high level of carbon monoxide wins the competition. But that's not the case in real life, in here, because the level of carbon monoxide is very low. Okay? It's very low. So that's why an oxygen level is high. That's why oxygen wins the competition. That's why oxygen is always bound to heme. Now, what happens with the distal histidine is that if carbon monoxide binds to iron, the affinity of carbon monoxide to iron becomes even lower than that. Okay? So that's a protection mechanism. So it allows for heme not to be saturated with carbon monoxide. Okay? So the purpose of the distal histidine is to weaken the bond or the interaction between whatever binds to iron, whether it is carbon monoxide or oxygen. And that's a protection mechanism. So again, someone might say, well, wait a second, how is it that we do not die from carbon monoxide since it binds with high affinity to heme? I said one, because not only that the interaction becomes, or the bonding between carbon monoxide and iron becomes weaker as a result of distal histidine. The second reason is that there is very low level of carbon monoxide in air. So, that's why every year during winter season, you always hear about people dying because they leave their heaters on. صحيح؟ تركوا الصوبة شغالة all night long, so they die. So why? Because heaters produce carbon monoxide. It becomes at higher level or high level than oxygen. That's why they die. There's no oxygen anymore bound to heme. That's why when you see in movies, people, in American movies, people who want to commit suicide, and I'm not giving you ideas. People who want to commit suicide, what do? They sit in their car, right, and they extend a hose from the exhaust all the way to inside the car, and they close the windows, and they sit in the car. They turn on the car and they sit in the car. Why? To get CO, carbon monoxide, inside the car. So they die eventually. That's why also accidents happen in the US where people turn on their cars during the winter in their garages to warm up the car. They go into the house and then they come back out. And there's a lot of carbon monoxide inside. If they stay long inside, they die because there's no oxygen anymore. So, هلا عرفنا now the purpose of all of these, of the primary structure of myoglobin. Well, let's look at this plot. This is known as the saturation curve of oxygen binding to myoglobin. That's how it looks like. Notice how it looks like. It looks like this, and then it flattens out. Well, we call this type of plot hyperbolic. That it goes like this and then flat. Okay? So we call it hyperbolic. What it tells me is the following. It tells me that the affinity of myoglobin to oxygen is really high. It's very strong. Which makes sense because that's what we want. We want oxygen binding to myoglobin to be at very high affinity. So that oxygen is released only in cases of emergency when there's hypoxia. So that's one. Now in peripheral tissues, the level of oxygen is about 20 to 30. That's in peripheral tissues. So notice that at this level of oxygen, when the pressure of oxygen measured in torrs is about 20 to 30, almost 100% of myoglobin is still bound, saturated with oxygen. In lungs, the level of oxygen is about 100 torr. Again, 100% of myoglobin is saturated with oxygen. It's only when the level of oxygen becomes very low, there is really hypoxic condition, when it gets to low as like 1 or 2 torr, that you have this sudden release of oxygen to tissues. And that serves the purpose of myoglobin. Now, there is something that in biochemistry, pharmacology, physiology, always measure, which is the 50% of something. The y-axis represents the degree of saturation or the percentage of saturation or the portion of saturation. That is the fraction of myoglobin that is bound to oxygen. And we always look at this P50 level because it gives us an idea. Now P50, that is the level whereby 50% of myoglobin is saturated or bound with oxygen, is about 2 torr. That is at 2 torr of oxygen, 50% of myoglobin is bound to oxygen. And this is really high affinity relative to hemoglobin, which we will talk about right now. ISO. So hemoglobin. Hemoglobin is a tetramer. It's a tetramer. That is, it's made of 4 polypeptide chains. 2 of them are identical and the other 2 are also identical, but these are different from each other. Adult hemoglobin is known as alpha 2 beta 2. That is, there are 2 chains of alpha and 2 chains of beta, which is different than fetal hemoglobin. It's made of different chains. Okay? For a different purpose. We'll talk about it later, I don't know, this lecture or in the blood module. So, this alpha and beta, by the way, is just designations. يعني واحد اسمه محمد والثاني اسمه محمد والثالث اسمه محمد. Well, تشابه أسماء. So what scientists do is that whenever you have a protein that is made of multiple chains. They call the first chain alpha, the second chain beta. You look at another protein, well, they call the first chain alpha, then beta, then gamma. So they're just names given to chains. It doesn't mean that it's the same alpha chain or the same beta chain. So if you look at the hemoglobin molecule, it is a tetramer. It's made of 4 polypeptide chains. It looks sort of similar, each chain looks similar to the myoglobin protein. Each one of these chains has a heme group. So each hemoglobin molecule can bind to 4 heme groups. So each hemoglobin molecule can bind to 4 oxygen molecules. If you look at the structure of each one of these chains, well, the beta chains have 8 alpha helices. So it is full of alpha helices, just like myoglobin. Myoglobin also has 8 alpha helices. The beta chain has 8 alpha helices. The alpha chain has 7 alpha helices. So 1 alpha helix less than beta and myoglobin. But overall, each one of these, if you look at the structure of the alpha and beta, they are full of alpha helices. The question is now, how are these chains, the 4 chains, interact with each other? Remember when we talked about the quaternary structure, I said that sometimes you have different polypeptides linked to each other covalently by disulfide bonds, or they can interact with each other non-covalently as in hemoglobin. So in fact, if you look at the hemoglobin molecule, these chains, the 4 chains, interact with each other via 2 things. 1, hydrophobic interactions. So yes, you have hydrophobic amino acids on the surface, and that helps the 2 polypeptides interact with each other. That's 1. Also, you have electrostatic interactions between the 2 chains. Some electrostatic interactions. And these electrostatic interactions have a very important purpose. So, would you expect hemoglobin to have high affinity for oxygen or low affinity for oxygen? If it has high affinity for oxygen, well, it would go to the lung, it will be saturated with oxygen, but then when it goes to tissues, it does not release this oxygen. Well, if it has low affinity, then if it goes to lungs, it doesn't get saturated with oxygen, and there's nothing left, or there isn't much that can be released in peripheral tissues. So in fact, affinity of hemoglobin towards oxygen is actually dual. Both. It has high affinity state and a low affinity state. In other words, it has 2 structures. It has a high affinity structure and a low affinity structure. So if you look at the saturation curve, it looks like this. This is for myoglobin in black, and this is for hemoglobin. Well, if you look at it, it looks like an S, the letter S, and it's called, and this shape of plot is known as sigmoidal plot. So a sigmoidal plot looks like the letter S. But what it tells me, what's important is, what it tells me is that there are 2 states. That is, you have a state right here, which is known as a low affinity state, that is, hemoglobin has low affinity, and then there is a transition whereby you have a high affinity state. And that makes sense. So that in lungs, you have a high affinity state whereby hemoglobin becomes saturated with oxygen, but then when it moves to peripheral tissues, it has a low affinity state so that oxygen is released in peripheral tissues. And the P50 is 26. It's calculated as 26 torr. That is what? That is at 26 torr, 50% of hemoglobin molecules are saturated with oxygen. Which is different than myoglobin, right? We said that for myoglobin it's about 2 torr, which means what? Which means that at lower level of oxygen, 50% of myoglobin is saturated versus hemoglobin. In order to fill 50% of hemoglobin or to saturate 50% of hemoglobin, you need more oxygen. Why? Because it has lower affinity. Okay? So that's basically what it means. So again, if you look at the plot right here, you see that there are two states. You have a state here that is a low affinity state. We call it a low affinity state, and you have a high affinity state right here. In the middle, you have a transition state. That is, you have a intiqaliyya. You have this change in the structure of the molecule. So hemoglobin has two structures. Yes, hemoglobin has two structures. And this is similar to other enzymes and other proteins that we call allosteric. Allosteric. Steri means shape. Allo means different. So allosteric proteins are proteins that have different shapes. In case of hemoglobin, it has a high affinity state and it has a low affinity state. The high affinity state is known as the R state, and R means relaxed. The low affinity state is indicated as the T state, or the tau, or the tense state. So the idea, if you want to imagine it, you have the tense state. The molecule is tense. Its arms are wrapped. It cannot bind to oxygen. Low affinity state. But in the relaxed state, arms are free. It can grab and it can bind to oxygen because it is relaxed. Okay, so you have these two states. The question is, how does hemoglobin go through this transition between the high affinity state and the low affinity state? Okay. Near? Be quiet. So you have a high affinity state and a low affinity state. The question is, how does it go through this transition from high to low? What happens is there is break in the there is a break in the electrostatic interactions between the chains. So let me move here. So what happens is you have this change of structure where when oxygen binds, there's a change in the structure of the protein overall. Now the electrostatic interactions that exist between the chains get broken up or broken out. Okay? So why does this happen? So when you break the electrostatic interactions, the molecule becomes relaxed. Okay? And it goes through this transition from T to R. The question is, so why do these electrostatic interactions break? Because of this is the beauty of biochemistry. Because there is movement of only 1 nanometer. That's it. Just 1 nanometer. Movement of what? Movement of the heme group. I said that heme has a flat structure. In fact, what it looks like a dome. That is when it's free of oxygen. Notice that you have this link between the iron and the proximal histidine. So what happens when oxygen comes in and when it binds to iron, the structure of heme goes through from the dome structure to the flat structure. So you have pulling down the iron, so it becomes flat. When you pull down the iron and you pull down the heme, it becomes flat. You also pull down with it the histidine, the proximal histidine. When this is pulled down, you also change. You have a gradual movement of everything else. So when this looks like a dome, and oxygen comes in, heme becomes flat. You have a change in the structure of heme that pulls with it the proximal histidine. When this is pulled, it changes the structure of the alpha helix, the whole alpha helix. When you change the structure of the alpha helix, the tertiary structure of this polypeptide that is now bound with oxygen also changes. When it moves, when it changes and it moves, it breaks the electrostatic interactions between this polypeptide and the polypeptides that are next to it. And when you have this breaking of the electrostatic interactions, the other two polypeptides also change structure as well. So it's almost like you have someone grabbing your finger, and this person turns your finger and says, anything? No, I don't feel anything. Well, turn it a little more. So now you have the alpha helix now changing the structure of the whole arm. Turn it again a little more, well, you change the structure of the whole molecule. So it's gradual change in the structure of the protein, of the overall protein, only by turning little turn of the finger. So what happens again? Heme is dome-like structure. Oxygen comes in, binds to iron. Heme becomes flat. It pulls down the proximal histidine. The proximal histidine changes the structure of the alpha helix. The alpha helix changes the tertiary structure of the polypeptide. That breaks the electrostatic interactions between this polypeptide and the two other polypeptides next to it. That changes the structure of the whole molecule. So you have this transition of hemoglobin from the T state to the R state. Now, this doesn't happen in myoglobin. Why? Because myoglobin is a monomeric protein. So this change in structure, this allosteric change in structure, only takes place in proteins that have quaternary structure, that are made of multiple polypeptides, 2 or more. Okay? So it doesn't happen in myoglobin because of that. And that's why you have this transition. That's why you have this transition from the T state to the R state, from the low affinity state to the high affinity state. Now this jump also, or this change from the low affinity state to the high affinity state is also gradual as well. What does that mean? It means that when one oxygen molecule, when it binds to one polypeptide, it makes it easier for the second oxygen molecule to bind to the second one. When two bind to hemoglobin molecules, they make it easier for the third oxygen atom or molecule to bind to hemoglobin. When three bind, then it makes it even easier for the fourth oxygen to bind. And this is known as cooperative binding. Okay? So this is really important right here. So when we say cooperative binding, it means that when one binds, it makes it easier for the second to bind, and so on. And the same concept applies to enzymes, to allosteric enzymes. And we will talk about those, inshallah, this week or the next. Now, this is also, by the way, protective. It's a protective mechanism, having these two states. The reason is, now if you move from sea level to high altitudes, in high altitudes you have low pressure of oxygen, right? Well, the pressure changes from 100 to 80, but that does not affect binding of oxygen to hemoglobin because it's still in the high affinity state. So you still have enough oxygen inside your body. But then if you exercise, and the pressure moves all the way from 80 all the way to 40. Now notice the difference in oxygen binding to hemoglobin. Oxygen is released immediately in peripheral tissues because of this transition from the high affinity state to the low affinity state. Even if you exercise, the level of oxygen in tissues actually becomes even about 20 or even lower, so more and more oxygen is released as a result of this cooperative binding and the transition of the structure from low affinity to high affinity and vice versa. Okay? And we're done with hemoglobin. Sit in your places, please.